Today we are very happy, proud, I don't know, confused to have here one of our heroes, which is Daniel Henry Holmes Ingalls Jr.
Thanks. You're too kind. Thanks. Yeah. Well, I may be in Argentina for the rest of my life because I have, among other things, because I have 5 names, and there weren't places in the airline reservation system to put them right. And so they're all different from my passport. So we'll see how that goes. Well, I am certainly honored to be here, and it's a joy just to see your country and wonderful people in it. And I'm especially grateful to Leandro for bothering me now for 2 years to come down here, and also especially to the folks from CORE who furnished my plane ticket. And I guess I'm going to try and move quickly through this so that we have some time for questions, but I think there's some extra slop tomorrow if people have more questions. And I want to not forget to talk a little bit about fun, because that's always been a part of Smalltalk. It's been a part of my life, and I think it's worth talking about a little bit. You know, where does the word fun come from? It comes from how kids are and how they play. And to me, a lot of that has to do with exploring the world. And I always tell people that I was born a physicist and trained that way too. And the part of that that's significant to me is being just loving involvement with the world, and often the physical world. And so it's what makes my interest in computers have to do with graphics and sound and media, as well as all the cool sort of abstract things like text and numbers and like that. Well, I'll just get started, and we'll see where it goes. I also want to give a quick bit of credit to my mentors, Alan Kay, who taught me to always try to have your cake and eat it too, or in other words, get the best of both worlds. If you have a conflict between speed and space, figure out how to get them both. And Don Knuth, who showed me that you should never fear, and in fact you should enjoy complexity. And Cyrus Harding, who is the hero of Jules Verne's book, The Mysterious Island, from which the Smalltalk balloon actually came. He was a childhood hero of mine. My father read me that book, but I really remember I was so much into it that he fell asleep reading it to me one day, and I picked up the book and read on, which is not easy. Jules Verne's text is very turgid is the word. With the Smalltalk work, I worked with a bunch of wonderful people: Ted Kaler, Dave Robson, Diana Mary, Glenn Krasner, and Alan and Adele, and Larry Tesler, and Trygve Rainscow. It was all a great crew at Xerox and at Apple. And in the Squeak work, I was most deeply involved with John Maloney, Ted Kaler, Scott Wallace, and then the entire open source community that grew from that, especially including the people in this room. It really is, and I mean especially because We had a couple of early people who did the ports, like Andreas Raab and Ian Pumarta, but it was the folks here in Argentina who really picked it up with its potential for, as a simple system that was malleable and that you could use for teaching, and a lot of great creative work done here. And then at the Lively Kernel, which I'll be showing a little bit, especially Christophe Palas, he and I wrote most of the Lively Kernel. Antero and Tommy did a bunch of applications on it. And also amongst our interns, especially Robert Cron, who's done a great deal of the work in the system, including a wiki built in it, which I may or may not have time to show. So I think the one thing, the relationship for me between physics and computer science is that I've always felt like I was sort of an inventor. And computers are just such a wonderful medium for invention. Because if you get a good idea and solve it, you can, a million people can be using it the next day or that afternoon. So I was going to skip through. Some of this stuff has to do with physics. My earliest encounter with computers, it seems a bit funny to be saying this, but my early experiences with computers, the computers were not the same. And I went to Harvard University, but they didn't have a computer science department at that time. But there were a couple of labs in the engineering department. And one of them had an analog computer from the war. And analog computers are great. And let me, there's a picture of one. That's not me. But you've got this patch panel with a bunch of plugs and wires. And you compute with the voltages on the wires. And the patch panel has these little modules that will scale voltages up and down, and then integrators and differentiators. And that's where you get the dynamic behavior. And then you see there's an oscilloscope there, a monitor, that you can measure voltages on and plot functions and all that good stuff. And I liked that because it was all so immediate. The minute you plugged in the wire, you could see what was happening on the oscilloscope. And then I read this book about a thing called the Bit Rate Multiplier. And this is, I'm maybe jumping ahead, but the idea is that you can take a train of pulses and feed it past a register and scale the rate of those pulses to be lower. And what this essentially gives you is the same kind of scaling you have in an analog computer, except you're dealing with pulse rates instead of voltages. And essentially the way you can scale it is by taking, if you have a register with a number in it, and the numbers coming down here go from 0 to 7, you can take the place at which the carry would stop, and that's these boldface 1s. And so you'll see that 4 times in this, the 1-bit is a 1, and 2 times the 2-bit is a 1, and once the 4-bit is a 1. And if you take that effect, and it with the contents of a register, then you can scale the rate of these pulses. And so I won't go into that anymore. But it gave me the idea that you could build an analog-like computer out of digital circuits. And just at that time, the first integrated circuits were coming out. They had done integrated circuits for a while, but the first ones that were affordable, little plastic packages that you could buy for $1. And I was jazzed about that. I had been doing experiments in my basement with sort of big circuits out of Army surplus. And this was really fun. Plus, they went 10 times faster than anything that had been available before. And I had this idea that you could compute logarithms by essentially wiring up an integrator, a differentiator, to give you exponential decays by feeding the contents by taking the pulse rate of the register to decrement it. That will make it decay exponentially. Or if you scale the increase by it, it will make it expand exponentially. So figured this out, and this is a slide rule. That's how a slide rule does multiplication. The distances on a slide rule are logarithms, and by adding logarithms, you multiply things. So that was the thing that my computer was going to do. And there it is. I built it. It's got a funny name. You know, I was a college student then. And it stands for Dan's Right Amazing Calculator Using Logarithmic Arithmetic. So I had an early flair for acronyms. And you can see this, the row of these little circuits along the top. This is the register that had the current number that was the rate of pulses, like the voltage. And this one down below held the accumulation of the logarithms. And this was a readout of the result. So anyway. And a cool thing about it was if you do a calculation on a slide rule, you can get a result. You can get a sum of logarithms that's greater than 1, so it doesn't appear. It sticks off the end. But somebody had the idea to build a circular slide rule, so that doesn't happen. So you always get the significant digits, as it were. And I was able in this computer to make it that the value in the accumulating register rolled over at exactly the equivalent of 10. So it would actually even always compute the significant digits. Woohoo. And so I worked with this little professor. He, as I say, this is in the engineering department and very sort of low-key at Harvard. But we submitted it to a contest for Massachusetts electronic manufacturers. And it actually won an award. And I was in Virginia building a hot rod that summer, and I got a call from this guy named Ann Wang, who was running Wang Computers, which later became a $3 billion business. And he invited me to come work there for the summer. And I said, no thanks, I'm having a good time. So, you know, it's like a sliding door. I don't know what my life would have been if I had done that, but I still wound up spending a good bit of time with computers. That spring, which was my last year at Harvard, I had my first computer course, which was where they taught us Fortran. And one of the simple programs they gave us was to print out the powers of 2. And I did a fancy job. I made it centered. Woohoo. And this was coming up to April 1st. And I wrote a program. Fortran cannot do infinite precision. You know, it's just got, I guess at that time we had 32-bit integers. And it also doesn't do a very good job of variable formatting. So I wrote a program that would print the powers of 2 up until it was the entire width of the printer. It was 132 characters. Printer, right? And I think it took about 30 lines of code. But I worked on it, and I got it down to 20 lines of code. And then I got it down to 10 lines of code. I finally got it down to 5 lines of code. Let's see here. Oh, yeah, I got to do. There it is. So this is the worst program I ever wrote. You notice the number of comments in it. And I left it on my professor's desk on April Fool's Day. Sorry, actually it's 6 lines if you add the end statement, but you didn't need an end statement in this system. And if you run it, that's what it does. It didn't go that fast in those days, of course. And I put it out. Some of you old squeakers, experienced squeakers, may know. I sent this out as a message to the Squeak list. Somebody had mentioned Fortran. I said, can anybody figure out what this program does? And Bob Arning figured it out. And what he did was he knew how Fortran worked. He wrote Squeak equivalents for all of these statements and actually got it to run. And this below is his program that did it. Okay. So silly stuff. But, you know, it was fun. And I learned a few things. And, well, I won't. Sometime we can talk about that. Let's see. it's a little bit difficult. For some reason, you can't go between the slideshow mode and other stuff very easily. Grad school, I won't talk much about. I was still sort of in physics, so that's me doing a project with a satellite that goes around the moon. They just put it up. And this one on the right is, I wrote a program. There was a computer that could measure voltages, and I had heard about Scientology, not the bad parts, but the kind of cool parts, which was measuring psychological effects through galvanic skin response. And I found a computer at Stanford Research Institute that had analog to digital converter on it, so you could read real inputs. And I wrote it's still Fortran, but I wrote a program that would kind of interview you and read your skin response and ask you more about stuff where you got a big response. And I've actually thought of returning to that someday because it's so easy to measure voltages with personal computers. I'm never going to have a problem with boredom. So let's see. I don't know why this is even in there. So I've got some experience writing assembly language. And Meta, if you guys don't know about Meta 2, it's the coolest system. It's right up there with John McCarthy's Lisp eval. And it was what inspired Alan and me in some of the Smalltalk 72 work, and it's what made us push Alex into doing OMeta. So OMeta owes some inspiration to this. And then my last Fortran thing was part of a project with Don Knuth, which was to study Fortran program behavior, just study program behavior, but we had a whole bunch of sample programs in Fortran. And what I did was, this is sort of like an early taste of reflection. So there's an example of a program that computes primes, and I wrote a program that would go through and insert statements in it that would count counters in an array and call a procedure before it was done. And it also put extra counters on if statements. And so it would produce a listing like this, which tells you exactly how many times every statement got executed, and it also showed if branches. And this turned out to be a really useful thing, and I dropped out of college, never got my PhD, but I started a company that would sell this program. And it was kind of funny because I went around to various places to sell it, and the big users of Fortran were the scientific users. And I said, look at this thing, it's great. It shows you what's happening, and you can save money because you can find out where your inner loops are and make your programs more efficient. And it turned out that most of the scientific installations, they didn't want to save computer time because they wanted to show that their computer was overutilized so that the government would buy them a new computer. But along the way, I came to some commercial installations who said, if you had this for COBOL, it'd be great. So I rewrote it in COBOL, and because those places like Safeway Markets only had COBOL, I had the opportunity of writing this system, this program editor and hash table statistics routine at the end, all in COBOL. So, oh boy, that was fun. Who knows? Maybe that's what gave us keywords. Then there was a little transition there where I was selling my measurement program, and I would go around to the different places in town where there were UNIVAC computers and IBM computers and CDC computers to make sure that my program worked on all of them. And came to one which was the CDC Control Data Computer Center, and there was a guy there he had a Fortran program to do speech recognition. And he had just been hired by Xerox PARC to do that. So I said, hey, I'll run my program on yours and you can find out where your inner loops are. So we did that and parted company. But a week later I got a phone call saying, I need some help setting up a system at Xerox PARC. Maybe you could come and work for me. So I got hired there doing that. and I had a lot of fun. I built him a whole sort of personal computing system out of a Xerox Data Systems mini computer. But the important thing was that across the hall from me was Alan Kay's office. And I kept being much more interested in what I was hearing across the hallway. And so eventually one day I walked across the hallway and started talking to Alan and got transferred, and that was the start of a long association. Let's see here. Don't need to talk about that. This was I've always liked small computers, and the fact is every time I get one, I play with it for a week or two and then forget it. But I think part of the fascination, apart from being a gear freak, is that, again, it's this fun thing, that here's this tiny little thing that has its own life. And the pocket computer was an amazing thing. It ran on two batteries, and this was a long time ago when there weren't many small computers around. And the one thing I did with that was it ran Lotus 123, and I figured out I had it on an airplane trip across the country, which took 5 hours. And I thought, now what could I do that would be fun? And I figured out that Lotus 123 can do, and all the spreadsheets now could do text manipulations as well as numbers. So I wrote a Pig Latin program that would translate English to Pig Latin. I don't know if that's going to make sense. Do people do Pig Latin with Spanish? Yeah. Okay, great. So that was fun because it was a program, so we can get into this some other time, but programming in a spreadsheet, it's like a single instruction, multiple data stream computer. And it's a different way of thinking. Anyway, I guess a lot of my then experience for the next 10 years or so was colored by my being at Xerox Research, where they had where they built the Alto and had the first bitmap displays. And sometimes people say, "Oh, you did such cool stuff." Well, the truth is that it was just a magical time. There was all this cool stuff waiting to be done, And a lot of that had to do with bitmaps and interactive stuff. And Alan had this passion for making a system that kids could use, and also this interest in doing a language that was all built around messages. At least the way I put it together, and he may have it differently, but he had just come from doing a stint at the Stanford AI project, and there they had a number of different computers which they, in order to make them work in between, they had to basically come up with message-oriented protocols. And I think this started to work in Alan's mind, and he thought, you could do a whole language around that, and wouldn't it be cool if sort of everything was that way? And I guess that's sort of how we came together. I was weird enough to be doing Pig Latin in a spreadsheet. So certainly doing numerical computations by sending messages wouldn't be that weird. So Alan had this idea for a simple interpreter that would work that way, and I built the first one. I guess I actually did the first one in BASIC, and this was because, well, I won't go into why, but got it working, and then let's see what's next. And so once we were clear about the fact that it would work, then I recoded it in what was available at the time, which was the assembly code of the Alto, which was also the assembly code of the Data General Nova computer. And I'll just show you a bit of that here, if I'm lucky. So some of you may have seen this. There is this implementation in Squeak of Smalltalk 72 that I did, actually for Alan's birthday. And let's see here. And it gave you this little window in which you could type text. And well, let me actually show you. This is the bootstrap of it, and So this just, we would read in all these definitions, and including, arrays, strings, and so on and so forth, and a file system, and a text editor, and all that good stuff. And here's a piece of code that will just give you an idea of what it looked like, and it's the definition of, it's probably hard to read that, but you don't need to read it all anyway, and maybe I can do this thing. Yeah, whoa. I like that. Okay, that's the turtle theme. Okay, so in this language, Smalltalk 72 is a beautiful scripting language, and it's just you read the incoming text and make it into just a bunch of tokens, atoms in Lisp, and you have these little operations. So this is a function, but it's also the description of a class, and we may or may not get a chance to see how you do both. But this little token here means if you see. So that token, when you're running this code in the class, looks up at the message stream that called you, and looks ahead and sees if that's the next token. And so the way you read this is, if you see pin down, then set my pin to be 1. If you see pin up, set my pin to be 0. And this hand is a quote sign. There's some really funny characters, and you can blame Alan for that. But it was sort of iconic. It means the next thing, literally. And here's one that says, if you see ink, then look for a left arrow. And if you see, and whether you do or don't see it, this means don't just look in the message stream, but start the message stream evaluating until it returns a value. And bring that value back and bind it to ink. So this colon having to do with evaluating the next parameter lodged in my head when it came around time to make something compilable. Anyway, the wonderful thing about this was it let us explore a sort of an object-oriented model before anybody had them. And you can see we started pretty quickly laying things out as the message protocol along with the code. And then I think that's as far as I'll go with that. And it then became the basis of a system to build educational software with, and the kids could do stuff like saying for I to 400. We had this built-in guy called Smiley. That's the turtle. Go I turn 89 degrees, not quite a right angle. And it would do stuff like that. I don't think there's much more that I want to show you about that, except that it was lots of fun. Kids could right away do cool geometric things. And the kids did a bunch of cool applications. We learned a lot about Smalltalk, and Adele and Alan did a significant amount of work on curriculum and stuff like that. Smalltalk 76, I wonder if this is going to go to the right place. I don't think so. Oh, let me just summarize Smalltalk 72. And it was really slow because, that system, it basically was parsing as it ran. But it was totally dynamic. It was a chance to learn the object-oriented style, and we built around it a graphic system, music system, animation, all sorts of stuff. The bootstrap was just 20 classes and about 200 methods, and it was tiny. So this all ran in 48K altos, which is 48K words, which were 16 bits, so it's like 96K bytes. I think that's about all I'll say about that. See where we go from there. So from there, I tried to have an emulation of Smalltalk 76, but I haven't succeeded in doing that yet. Smalltalk 76 had a complicated but very cool virtual memory in it. It was an object-oriented virtual memory. And my claim to fame, along with Ted Kaler, was that when we designed it, Butler Lampson said, "You'll never get it to work." And we got it to work really well. But then from Smalltalk 76, I guess, let's see, what do we have to say about Smalltalk 76? I'll go back here and at least tell you about it. It was my favorite sort of flash of inspiration. I came up with the whole idea for how Smalltalk 76 would work. I mean, of course, there was lots of thinking going up to this, but on a weekend at the seashore with my family. The idea of getting something that looked like Smalltalk 72 code, which we had these buzzwords. You could put words in to make it sort of read more like English. And I came up with the idea for keyword syntax. Not totally. I had seen it elsewhere, but not used in programs, used in data. The idea of compiling it to bytecodes, and there were several things that we had experienced with Smalltalk 72. Smalltalk 72 did not have inheritance, and we wound up copying protocols of array into strings so that you could do the same kinds of things. And classes weren't first-class objects, and by that time we knew that we'd like to do things like class new and so on. And contexts weren't real objects, and I just knew that it would be incredible if they were, because you could write the debugger all in the source language. So anyway, this all sort of came in a flash, and we set to work on it, I and the trusty crew. And I think it went incredibly quickly. I think it took us about 4 months before we had something actually running. And I'll never forget, this is a joke between Alan and me, which is on the day we got it all running, Alan had been working on this other scheme. And he came into the office and said, "I've got this great new scheme." And I said, "Get out of here." So anyway, where should I go from here? Let's just I'll quickly show you. So there's Smalltalk 80, and actually I think a lot of you have seen this. There's a version of Smalltalk 80 that Vasily Bykov did in his Hobbes system, and I got it to work in Squeak. And so you can, there's the browser running, and it all just works. In fact, it runs faster than it did on any of our computers when we got it working. And then there's another version. Having done that, I got it to read in the Apple image, which was also part of the Xerox Smalltalk release, and it actually worked somewhat faster. But that's because we had spent some time tuning it. And the other thing that's notable about this is that this is a one-button interface. So in the Xerox image, you have to use control keys to get menus. But in this one, there's you don't. Let's see. Oh, wait a minute. That's the trouble is I'm still looking at the Xerox one. I knew there was something wrong. Yeah, there we go. So. Oh yeah, here we go. Sometimes I forget how these things work. So you could do this all with a single button. So by putting over a part of the scroll bar that would give you a button, you could execute things that way. And let's see if I have any examples of things to run here. Oh yeah. Here's an old favorite. There we go. So, and that's actually running separate code for every pixel. So it's actually performing decently. Anyway, what's to say about Smalltalk 80? Well, we got a chance to clean up several things from Smalltalk 76, and there was one in between called Smalltalk 78, which we built to run on a little 8086. It was sort of this was in the first year or two when microcomputers came out. And Smalltalk 76 had run slowly because it had an object table that was hashed. And this was to support our virtual memory because there wasn't room for everything in memory. So it would take an OOP and hash it and then bring an object in if necessary. So we went in Smalltalk 78, we went to direct addressing. Sorry, I've got the wrong slide up there. But we went to an indexed object table. And also, I had just gotten BitBlit working, and it allowed us to the whole motivation for BitBlit was that we had code around for doing line drawing that was doing pixel stuff, and windows of arbitrary size, and text display, and it just, all of the yucky code was doing the same kinds of stuff, and that inspired me to do BitBlit, and I'll come back to that. But that allowed me to make the kernel that much smaller. So the entire interpreter for Smalltalk 78 was 16K in memory of assembly code. And Smalltalk 80 basically was the same as those systems, except that we came up with the Boolean class, which that was a fun invention, and did blocks a little bit differently. It got standardized to use ASCII. So those funny characters went away, all except for the left arrow. And there's the size of the system as it was released. It's 200 classes and 5,000 methods, and 200K in code bytes for a 2.2 image size. And it's one of the things that felt really good to me about Squeak was, maybe I'll get to this later, but even in a 32-bit system, we actually got images that were smaller than this. So let's see. I'm going to go out here for a second and okay, I think I said most of that. Yeah, so there's BitBlit and the job it does, which is taking arbitrary rectangles out of image data that's encoded in, consecutive words, and taking care of all that trouble. And it was a wonderful motivation at Xerox PARC to have micro-coded computers, because it meant that if you figured out some little kernel that would do something useful, you could get it to run 5 times faster than regular code. And it allowed you to sort of almost give the machine a different feel. So that was what BitBlit was a kernel that would fit in the microcode. And so was the interpreter inner loop of byte-coded Smalltalk. That was part of my motivation there. The thing I figured out about BitBlit, I got this idea after leaving work. This is when I had a lot of my creative ideas. I'd leave work, get on my bicycle, and my rational mind would stop, and everybody else would get a chance to talk. And the idea here was that you could, if you think of one of these as being the source and the other being a destination, and this being a sort of like a printer's wheel that picks up the image and lays it down, it made it clear how you could do this all with no temporary storage except for 2 words in this circular register. I had lots of fun with BitBlit also because, it gave a lot of power in the image space on bitmap displays that we hadn't had before. This is a project I did with my father, who's a Sanskrit professor, and that's some Devanagari text on the screen, and the black marks on the left are a histogram of how many pixels are black in that line going down. So that was enough to tell you how to break the page up into lines, and then you do the same thing horizontally to break it up into words, and then down below here's a word, and you do the same thing coming down in the word, and you can find this horizontal line called the matra, and the things up above are vowels, and the things down below are consonants, except that there's some more vowels below the consonants. But anyway, and then having done that, you can go along and break the actual bottom area up into its separate consonants. So this is called the segmentation problem of OCR. And then the question is, how do you recognize an unknown? And what I did was to take a bunch of instances of the same character. In this case, there's 4 of them. And I made what I called the skin and bones. And the skin is, you basically just and, so all the black pixels get anded together. And you get this thin area that if you see another one of these, this is the character for T. If you see another one, it better be black there. And you also make the bones, which is it's the OR of all the black pixels. And if you see an unknown, it better not have a pixel outside of that. So you can actually do optical character recognition, and this is an example of that working. And this is an example of that word recognized, and that was a fun project. So there's a video about that that I can steer you to. I think it's on the Wikipedia. And then another fun thing I did with BitBlit was this Conway's Game of Life, where you've got a bunch of cellular automata, and there are rules for cell's survival depending on a count of its nearest neighbors, of the 8 nearest neighbors. And it was hard to do. One of the neat things about BitBlit was it was a high-speed computational engine embedded in some not that high-speed software. So I figured out how to do the game of life for an entire pixel image. And here's the picture of how it works, which is you actually have separate bit planes representing the 1-bit, the 2-bit, and the 4-bit of the number of neighbors. So you slide it around and do adding operations using BitBlit. And then and these are the carries. You need a couple more pixel planes for the carries. So in just doing something like, I've forgotten, it's about 30 BitBlits, you can do the entire game of life for a million cell array. And y'all may have played with this already, but it's always fun to see. So that's running a 1,000,000-character array. And you can see all the little things. If you know this game, you can see recognize different patterns. Okay. Oh, yeah. And then when we got to Squeak, so Squeak was really fun. Another one of these flashes. When I remember I was driving home in the rain, and I knew I was going to. I was about to leave interval research and about to start work at Apple, and I thought, oh God, do we have to recode that interpreter again in C? And those of you who know me know I've had it as sort of my goal to never have to learn C. I mean, the truth is I sort of understand it, but I've never gotten into it. And I had this idea that things were fast enough that we actually could get it to be usable by running the interpreter that we had put together for the Blue Book as a sort of a reference description. And then that we could translate that to C because it was written exactly that way, and we could do that automatically. So we had this incredibly fast, like, couple of months when we got all of Squeak running from scratch, starting with the Apple image. That was a lot of fun. And then during the summer, I got BitBlit working, which gave us, I had to extend it to color because I hadn't had that before, and we wanted to support all the color depths and the pixel version of color versus the other kind. And then had this flash when I was away at a little conference in New Hampshire about how to do rotations and scaling too. So I added that, and that became Squeak. And what's there to? Let's see. Yeah.
What does DDA stand for?
Oh, DDA. DDA stands for Digital Differential Analyzer. And that's the thing that I showed you at first, this way of computing logarithms by feeding the contents of one register into another. You can actually do that, so you can build numerical computers that way. And it basically, it's the idea of having, of modeling a bunch of numerical quantities that have, hardware rules for what their next value will be, and you encounter that. For instance, if you take a look at the way to make circles really fast, what you do is you set the increment on the x value to be a small portion of the y value, and the increment of the y value to be the negative of a small portion of the x value, and it makes a circle. That's computing a sine with a digital differential analyzer. And with WarpBlit, it was the idea of, if you want to scale it, then you set the scaling, and when you scan across the source, you move at a different rate, and then you put the pixels out to the destination. And similarly, you do stuff with rotation by mixing x and y. Thanks. So let me go back here and get rid of that. I just realized, I work always with this particular Smalltalk image because it has free cell. And I will never tell anybody how many times I've played free cell. But it happens to have still on it a bitmap of South America. So I see it was all working up to something. I had that image because years ago I wanted to scan in some map data and make morphic objects out of it. And it was... You have to be tricky if you want to find the outlines of stuff where the colors aren't all the same. And this brown is not uniform. It's got different colors in it. But they're actually, I don't know if this still works in Squeak, but if you say new morph, grab flood area from screen, you can go over and do that. And it does a pretty good job, Isn't that great? Yeah, so that's a BitBlit hack. Another BitBlit hack, and WarpBlit, for those of you, this of course has been so much in Squeak, I'm sure everybody plays with it, but I love this thing. So this is just saying, take the screen and shrink it down, and have the scale be the vertical position of the mouse, and have the rotation be the horizontal position of the mouse. So you can do all this fun stuff, and you can play music and so it goes. I've spent a lot of time with that too. It's all fun. Okay, let's see what's next. How are we doing here? Yeah. I think that does it for Squeak. I'm going to go ripping through the lively kernel, and then I'll stop and we can do some questions. So a lot of you know that I haven't been working on Squeak recently, but I went to Sun Microsystems, and for a while I didn't know what to do there, but it seemed like doing stuff with the web would be fun, because everybody's doing stuff with the web. But I looked at what it was like, and I said, how can this be fun? It's like HTML and CSS and PHP and all these protocols. And it was so much easier 30 years ago, What do you need? You need a dynamic programming system, a dynamic language, and some graphics, period. So that was the idea behind the lively kernel. And let's just see where we are here. I think the easiest thing to do. So here's a lively kernel screen. And the lively kernel, so what we did was we just took JavaScript and coded up a simple little morphic environment. And so these are rectangles, and the basic graphics in browsers give you the basic shapes. We used SVG, but I actually recently just got it all to run with Canvas instead. And so you can imagine it's pretty simple to write the code needed to pick up an object if you click on it and move it around, and similarly simple to duplicate things. And the standard demo I do is this thing and then it's also pretty easy just to put a handle, which is another movable object, on stuff, and do this. And so you can do simple editing of shapes, and a simple drag and drop rule for composing. And we're just talking a page or two of code here, and now you've got a new object. And then one of the nice things about browser graphics is you get nice anti-alias scaling for free. I mean, I guess it's free. And you can rotate things too. And then here's an object that has a little script, a ticking script that makes it rotate, and you can have fun with dropping things on that. So, all of this stuff, and you can. It's also fun to take this, and you can do. Let's do something like that. Take another one of these. Put it on there, and pick that guy up and put him on there. There we go. Okay. So that's fun, right? Much better than HTML. And hey, guess what? It's a web page, right? So then from there, this development tools. Actually, is that where I want to be? Yeah. Let me close a few of these things. So besides the graphics that it comes with, you can also write little scripts. Oh yes, and take this thing, and it's really nice having arbitrary scaling. That is nice. So this you'll recognize. Create a new pen, set its color to red for I from 1 to 40, increment I, and tell the pen to go that distance times 2 and turn 89 degrees and draw the result. So if we say, there's the result of that program. Sorry, I hit Command S in there. And we could have made this be 400 and this be blue. And the cool thing about this is that these aren't just marks on the screen. This is an actual object, so I can pick it up and move it around. Actually, I think I'm going to delete it because it's pretty big. But so it isn't just that you can write fun kids programs with this, but what I've just done here is taken a little piece of JavaScript, tried it 2 times. To see the results, made a couple of changes. So this could have been something that was going to a URL to find your stock price, and I just sort of had a chance to try it out and debug it. You can, of course, do nice geometric designs. This is one of my favorite ones. It's the interlocking Hilbert curves that I did back in the first Smalltalk, and it's fun because you can. Let's see, how can we do this? Forget that. And here, if you take the the text that we've got and put it in a list and add a little script and add a little bit of MVC. You can have interlocked lists. Here's a rectangle, two rectangles embedded with a little script that gives you a value slider. And if you turn that slider on, it's, well, actually, you write it in a general way so that it works this way, right? And then you can use it as a scroll bar. And the only thing I haven't shown is a clipping component. So you take the list plus the scroll bar and a clipping component, and you've got the kind of stuff for doing real software. And you can actually go and look at clock morph. Let's see. Let me go back here. If I take this clock in this world and drag it down here and into there, boop, then I can go and look at the code for how the clock works. And here you see it says, first it gets the date, the current time, sets the hour hands rotation to be blah blah, the minute hands rotation, and the second hand to be the current second divided by 60 times 2 pi, right? And you can be mischievous here and type a minus sign, and you got a clock that runs backwards. So the point of that is just that it doesn't take much to put enough of a system together that you can actually look at itself and change itself. And with a little bit more work, you can have it save itself on a page. So you've got you've got an entire lively kernel. And so this, the inspiration here was, again, and this is something that Alan and I both come back to all the time, which is making something that's small enough and simple enough. This system is, it's about 10,000 lines. And of course, it's simpler because it doesn't have to do all the graphics. But it is something that you can give to a college student and say, find out how this works and play with it and change it. So I think that's kind of inspiring. And there's a lot of other fancy software in here. There's a whole client-side wiki implementation where you can save pages, but you save them into an SVN repository, so you can go back to old versions. And let's see, what else is there that I can... So I can show you more of that stuff, but basically that's, if you just go to that website, you can find out about it. Let me... Somewhere here I have a slide about what the future work is, which I may as well refer to. Oh yeah, so if I'd be happy to talk about fun with writing interpreters sometime. And Fabric I haven't showed you, but oh boy, there's some stuff for tomorrow. Squeak, lively kernel, yeah. So we actually have a version of Fabric that runs in the lively kernel, and this wiki, which is mostly the work of Robert Cron. It's about 10,000 lines in the kernel. There's lots more code that's written in various applications. Future work, one of the things that was bad about the lively kernel is that it was a world unto itself. And this has been one of the serious problems to overcome with Smalltalk. And we finally figured out how to make lively kernel elements in regular HTML, so that's really nice. It means that you can sort of take on the role of being a dojo, that kind of thing. And I got it to work on the canvas graphics, and that was a lot of fun. It actually makes it much more like the Squeak scheme, where JavaScript is handling all the damaged rectangles, and you can see that on the website. We got this idea to do language skins using Ometa, and that we just got started on that, and Alex and I keep not quite having time to sit down and work on this together. But the idea is, here's a system that's all written in itself. It's all written in JavaScript, and on some of the modern interpreters, it actually runs fast. And you can decompile, you can parse JavaScript into a parse tree, and you can print the parse tree out into Smalltalk or Scheme. Now, there's some things that don't transfer especially well, but I can tell you that the guy who wrote the lively kernel was writing it in a Smalltalk style. So that's actually a doable thing. So that's one of the things we're going to play with, and we thought, wouldn't that be cool, again, if this is a system you give to college students to play with, they can also look at that language independence and what's different about the languages. And of course, there's some languages for which you can't do this. But the cool thing about it being a complete self-describing kernel is that the minute you get the skin to work, you're looking at the whole system in that way. Collaboration, the early version of this was a multiple hand morphic like Nebraska. And we somehow let those bits rot when we did the first SVG implementation, and I want to get that running again. And then the other experiment that I want to do is to do an implementation with a decent performing plugin like O3D or Java 3D. And O3D is especially nice because it has the V8 interpreter in it. And right now, if you look at the lively kernel, it tends to be a little on the slow side, but almost all the slowness, lack of speed, is due to going through the document object model to get the graphics done. And I'm going to stop now. There's a couple of other fun demos I could show you, but we can do those offline. Let me take time for questions.
I have a question.
Okay, good.
I have many questions.
Yeah.
Now, one of them is, when did you realize that it was a good idea to have a system reading itself? I mean, for Smalltalk, the meta model is written in Smalltalk, and now you are doing the same thing with JavaScript. When did you realize that having a language reading itself was a good idea?
Yeah, that's a good question. That didn't come as a flash, but it came. It grew out of having a system that was lively. So, and the first system that we had like that was Smalltalk 72. And the thing was that it's such a viscerally good feeling to have stuff respond immediately to your changes. And the minute you have that kind of work going on, then of course you're also building a system. So every once in a while there's some aspect of building the system that you do right then and there, and maybe you're changing something. So maybe you're trying to add a class variable in Smalltalk 72. You figure out how to do that, and you think, "Whoa, that was clunky. Why couldn't I just send a message?" And so you start to think that way, and then doing a debugger in Smalltalk 72 was just unapproachable, although I had this code that would go down and try to get memory addresses and read the memory addresses out, hoping that nothing got moved and stuff like that. And then you realize again, so if this were described in the system, so it comes out of this experience of leverage and wanting to use leverage. And sometimes it takes you in silly places like that warp-lit mandala, which is just silly. But other times, the leverage, that, I could use this leverage to do all this other stuff that was hard before. Other questions? Oh, come on, guys. Yeah.
Nobody else.
If you're all just afraid to, also, you can. I'm going to be here for days, so.
Okay, the other question I have is, what is the interlocking meta model of Smalltalk? I mean, the class and the meta class, because I know that we had a simpler one from Smalltalk 76, I think, or 74.
Yeah.
And then you changed it. Would you do it again? Would you change it and simpler again? Because, teaching that meta model sometimes is hard, and I know that there is something going on there.
Yeah, it's hard to say. So I can tell you how it came about. Yeah, which was it came about for a couple of reasons. But we had various classes wanted to have special initialization code associated with them. And then there was also this sort of theoretical notion of, this came from Adele and teaching some kids. She said, I don't want there to be any uninitialized points. No points that are nil and nil in their x and y coordinates. And so this was a way to do that. Now, you can do that all without metaclasses, but if you want to do that kind of thing, the place you got to put that code is in the class. And if you have only one class, then it gets full of this garbage that belongs in all these other different classes. So that's how it came about. And if you want to know about the hierarchy and how that works, that's my fault, because Adele said, I want this, and I said, if you want that, then this is how it's going to have to work. And I had to think about it for a while that night. And in the morning, I put the diagram on her door. But I think the idea is that you don't, people say, you can't teach that to novices. Well, of course you can't, and you shouldn't, but you can say this is how you create points, So that's kind of how it came about. And you see the same thing in JavaScript and Java. I mean, it's like static methods and who knows. Anyway, that's how it came about. And yeah, I think it is simpler. So I've thought of having the JavaScript here not have class-side methods, or to not put a switch in the browser, but to distinguish them in the list with a mark. So who knows? Yeah, but there, go. So, yeah. So, what I hear you saying was...
Once the first stable version of smalltalk,
yeah.
I believe the 76 how was the academia response to it? How was it received?
Yeah. Well, let's see. Alan could answer that better than I can, but I can tell you the various things that I remember. And it depends also what you call academia. But for instance, we had an association with Seymour Papert's group at MIT. So they were aware of this, and they thought it was really cool. And they, the thing that first got them excited was the idea that, you could have multiple turtles. And that is cool. You can have multiple turtles, and it's really fun. So that was one. Then there was the Simula Crew, and I don't know. I'd be really interested to talk to them from this standpoint, and I never have, although I've chatted with them. But I always wondered. I think sometimes I think they were a little bit envious because they had done all this hard work about simulation and object models and stuff, but all in this static world. And here we were just having a ball and modeling graphics this way and all sorts of music this way. And it was like, sort of, they should have gotten credit for all that, but we're doing this cool stuff. I don't know. I think they were excited to see it happen. And the credit certainly does go to them for a lot of the early thinking about that. Let's see, other academic. So another one is the name that leaps out at me is Carl Hewitt, because Carl Hewitt had been working on the actor model, and it was in many ways, simpler and purer. And somehow he just didn't have a crew around him that made this stuff real and fun. I mean, I think it launched us to be doing real stuff, with graphics and music and all that fun stuff. Yeah.
So about the language level, I'm wondering what is the difference if you take Squeak, you take the rendering or graphic system? Because for me, I really don't see the difference. Why would you jump on JavaScript? Just because the method much time.
Just because?
The method savais.
I jumped on JavaScript because it ran in every browser.
Flash. J'ai appris.
I was working at Sun Microsystems. And Sun was specifically interested in, in alternatives to Flash. And many people are currently interested in alternatives to Flash. So that's part of the answer. But go ahead.
Yeah, but you could have done exactly the same with Squeak.
At that time, I couldn't have made it run in every no. Yes, if you download a plugin, right? But there's a big barrier there. What about schools that aren't allowed to install plugins? What about being behind firewalls and all this stuff? So I don't know. It seemed to me that was the way to get things going.
But if you wouldn't have that limitation, would you use Squeak or JavaScript?
Well, so then you get into this other area, which is political, basically, or is it social? It's the problem of the dark horse language, and there are millions of people doing stuff with JavaScript. So there's the opportunity there to get into that. And I I almost think it doesn't matter. The important thing is dynamic stuff and getting everybody's consciousness raised about that. And I don't know if the web will go the way of the lively kernel or what, but by God, the people who build hardware make sure that it is dynamic. You can change everything there in a nanosecond, and we ought to be, building systems that are that way and that end users can do that kind of thing with. And I kind of think that, down the road we may come to some consensus about what language we want to use, whether it's JavaScript or Squeak or something very different, I wouldn't turn around and do that right now. If it had been possible to run Squeak without a plugin, I probably would have done that from the get-go, yes. Yeah. Other questions? Yeah.
Regarding the same, I saw your discussion with Avi Bryant about, not really discussion because we agree, about what he did to run Smalltalk on JavaScript in the browser.
Yeah.
So do you think, you could have done it, of course, but do you think that related to the previous question, that it's interesting to follow that direction, or that the syntax doesn't really matter if you have the tools?
Yeah, it's good question. So people hear that. The question is, does the syntax matter of Smalltalk versus JavaScript? And it was Avi Bryant was the person who got me going again on this idea of doing skins on top of the lively kernel. And I think the syntax does matter. And you know what I like. But it's hard for me to answer, because all those millions of people out there like parentheses and commas. But I don't, they never had a choice. So it's hard to say. And then there's the question of the semantics that don't quite match up, and I don't know what to think about that either. Should I rewrite? Should I get rid of all the places in the lively kernel that use variadic arguments, or not? I don't know. But I'm interested to play around with it. And again, that's one of the cool things about the lively kernel being small enough, and about Ometa being lively enough that truly we can play around with this a little and see what we like. And it's been so much fun with this. When I started this project, there wasn't a JavaScript around that could come close to Squeak speed. I felt so good about that. And now, most of the browsers run equally fast or more even. So it's great to see that. And there's this story which is, when we were getting going in the project, I envisioned needing a fast JavaScript, and we actually, Antero and I both knew Lars Bach, and so we invited him to come to interview to do a JavaScript engine for us. And on that same trip, he also interviewed at Google. And you know who won. But the cool thing is, he did exactly what we wanted him to do. So that was neat. Yeah, exactly. Other questions here? Yeah.
So I wanted to ask you, I mean, do you still get on your bicycle, actually? You mentioned it was on your bicycle trips home, and I guess I was thinking, now that everyone's caught catching up, Ruby is looking a lot like smalltalk. Have you got on your bicycle and thought even further ahead? Is there something kind of even crazier that maybe inspires or you think we should do?
I don't have any wacky schemes in mind right now. And yes, I do still get on my bicycle. I love my bicycle. It's I weigh 10 pounds less than I did this spring for that reason. Although I may have it all by the time I go back to the States. But the thing I'm most interested in right now, and I'm really still quite ignorant about, is the work was started that I'm in touch with was started by Mark Miller in a language called E. And it isn't really just a language, it's an architecture. So, and those of you who are on the Squeak list will know that there was a project to do an E-Squeak. E is basically the idea of making it's called a language for secure distributed computing. And the idea is to get rid of the language, get rid of all the elements that compromise security. And the essential idea is really to do good object-oriented design, which is to say you do everything by capabilities. So if you're writing a procedure, the only things that come into those procedures are handles that have the permitted operations. You can write whatever code you want in there, but you simply have no access, no knowledge of anything else. And E couples that with some good thinking about what happens between the boundaries of distributed pieces of computation. For instance, dealing with computations that don't return right away, that are busy doing other stuff, and that's the whole idea of remote sends and promises. And this work is currently going on at Google. Mark leads that group, and the language that they're working on is called Caja, which is Spanish for box. You know that. But it's also CA for capability-based, JA for JavaScript. And the motivation for that, there have been a couple of attempts to make a reasonably secure JavaScript. And the reason for that is so that you can, if you're into this kind of business, so you can have advertisements running in JavaScript on a web page and have them not do bad things. So you want that to be done in a kind of JavaScript environment where you can't do bad things. And so I encourage you all to read about Caja and Cajita. And so one of the things I'm trying to understand, when I looked at E, which is an E version of Java, and E-Squeak, it bothered me. It just didn't seem quite as natural, as easy, intuitive to write things that way. But I'm convinced that that's the way of the future, because essentially all it's saying is it's like the internet all the way down. And I think that's how things are going to want to move. We're going to have, in addition to all our data out there in the internet, we're going to have all the processes that we have, and we want them to be safe and secure. Other questions? I'm sorry, what?
I know that you work at some problem with merging with Oracle within my perception. We understand that you might have some direction given by the broker, but how about mobile devices? We also have this.
Oh, mobile devices? Yeah, so I think they're great. I've got one. And my picture has always been, my picture with the lively kernel was always, picture somebody in an airport or at a bus stop, and they miss their honey, and they want to just draw a picture of a heart and say, thinking of you, turn it a little bit this way, put a nice red gradient in there, and then send it. That's what I want to do. And so the lively kernel is aimed in that direction. I want to make that easy. If you will, it's like Flash, but you can do it all in itself. You don't need a big Flash content creator that you have to pay money for, And it's all open web. So that interests me, and it's also the root of a project that we had going for a while with Alan Kay's group. I wanted Ian to do and we actually got some of this working, a JavaScript based on Cola, and also take Dan Amelang's graphics based on Cola, and put that all together, and that would be the entire kernel needed to run the lively kernel on top of that. So that together would be a nice simple system. And we never quite pulled off the last iteration of that. Yeah. Well, let's see. Let me see. Anybody who has not asked a question yet? Come on. Oh, yeah.
What do you think about trends in these 4 years? Result that has used technique, trends in technology.
I'm not sure if I heard this exactly. What do I think about Friends List?
Friends.
Oh, trends.
What do you think about trends?
And list?
4 years of technology. Do you expect it as we are now? You never talk about it, never this.
It's hard for me to answer you. It's sometimes I see things that are happening in technology, and I think, oh, that's a great idea. I want to work with that. And you could do this with that. And other times, maybe I get an idea of something that isn't happening, and I think, oh, I wish we could do that, and then try to do that. But I don't. I never strategize. I never think about that in the purely. It's always there's something I want to do, or there's something I see people doing. I guess I'm very concrete in that regard. But then when I see things that could be put together, I think, I think of wacky things to do, and some of them are useful. I don't know if that answers your question.
Yes.
Okay. Yeah.
You were
Yeah.
talking about JavaScript engine based on Golang.
I was talking about a JavaScript engine based on.
Yes, JavaScript engine based on Golang, and that with the live kernel would be an nice system. But you also said that the main reason for using JavaScript is because it is already in the browser. So if you use JavaScript because it is already in the browser, what's the point of
Really, what is the point of that? Yeah, I guess this came out of some thinking again about mobile devices, and Ian's not the same kind of guy as I am, but that's what I would have done, and I would have gotten it out. I would have tried to get it out to the market much quicker, and I think they could have made some money off of a small, fast JavaScript. And that, to me, was consistent with all the other stuff that's happening. You're right. At this point, it doesn't make a lot of sense. And that's why, we didn't quite complete the second iteration on this, and part of the reason is because Ian wasn't into doing it, and the other part was I thought, what's the point now? So, yeah. But I will tell you this much, which is Ian got a nearly complete reference interpreter running in Cola. And if you bug him, you might be able to get a copy of it to play with and maybe complete. Yeah. 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 Yes, over there. I'm afraid you got to start over. Oh, huh. Means it didn't work out the way I wished. Yeah. Yeah, there's probably a bunch of them, and, at all levels of my life. But I don't think there are any that I'd try and go back and undo. I've learned from all of them. So you mean maybe some things that we did wrong that we should have done a different way? So if I were farther along in this notion of secure object models and that whole model of computing, then I might say, yeah, I wish we had done that from the start. But I have yet to see that being as easy or productive. But if I imagine myself 20 years down the road looking back, I can't imagine that we'll be using unsecure computing metaphors. Just imagine a bank that's got two people coming to them, and one of them saying, well, we'll code it up in C++, Java, blah, blah. Or we'll code it up in Beauty, and Beauty is provably secure. What are they going to choose? So obviously, to me, it's obvious that the minute we cross that threshold, there will be a revolution. And I think it's going to take, and I think it's possible to do all that right now, except that it's not as easy to understand, it's not as easy to program. It takes a while for people to think that way. But I think we'll cross that threshold, and I think that will be a revolution. And I think it will be like the internet, sort of all the way down. There's also over beer this evening.
Dan, one of the fascinating things to me when you were talking about the 76 slide was the reification of context. And how you said that then it seemed obvious. And, wouldn't have seemed obvious to me what an inspiration that was. And as we talk about all these other technologies and how they're closing the gap, how the world is becoming more dynamic, and we're able to build logic kernel, that is the one area where I see we still continue to, as I consider the path along smalltalk-programming-language and discover the meta class hierarchy,
Yeah.
the point where you realize context is real objects too.
Yeah.
Explore them and send messages together is a huge life.
So that was.
I don't see that happening elsewhere around the world. Is it never going to because of security, or is it just not?
Oh no, I think there's ways of doing it with mirrors that can be secure enough. And that was a real sleeper because it didn't come to me in a flash, but in Smalltalk 72 there was a place where you could get at that state. So I knew that in Smalltalk 76 I wanted to have an object for that, and then of course there are these frames, so it all made sense. But what even at that time I didn't realize was how revolutionary it would be for the debugger. Because, I'm still thinking, oh man, now we got to do the debugger. And it was like an afternoon to get the first debugger going. So, that was fun. And, people emulate it in various environments, Eclipse, NetBeans, those huge things. I don't think we'll ever go back, on that. But it's really neat to be able to do that in just, a page of code. Yeah. Okay, why don't we take a break? You're welcome to come up and ask me questions. And I have one last thing to say, which it's just that this is exactly why we did Smalltalk. You guys here. So.